Hey everyone, welcome back to the continuation of our lesson on electric current. We're going to continue today with looking at a graph here between current and potential difference. We'll talk a little bit about resistivity of conductors and how that relates to the resistance through them. We'll look a little bit more about this relationship between current and resistance. In our previous video, we had likened the flow of electric current. Let's go with a black one here. We used a little analogy of electric current, how it relates to water flow. And I like to think of a lot of aspects of electricity in a comparison to water flow. I think they work very well together. So if you can understand water flow, you can understand how electricity is going to flow or have its flow affected through a conductor. So I took this graph here, I took the data here and put the graph together ahead of time so you guys don't have to watch me make a video on drawing a graph. So you guys can pause this and draw this in here, and then we're going to talk about this a little bit. So I have all the axes labeled here. We have a title on the graph. On our table here, we have our X, we have our Y. I drew a line of best fit between our 5 points with roughly equal numbers on top and equal numbers below that line of best fit, and then put in here to find the slope of this line. We need the change in y over the change in x. And I put those values here. We have a change in y from 0 up to 156, and the change in x from 0 to 1.0. And this is going to be 156 potential differences measured in volts over 1 amp. We get a total of 156, and that's for slope. But what physical quantity does this represent? Was a little bit of a review from our previous lesson. We know that the resistance in a conductor is equal to the ratio of the voltage over the current. So this 156 is going to be our resistance, and therefore we label this with our ohms designation. So the resistance of this conductor that has these current values across this potential difference has a resistance of 156 ohms. The physical quantity of the slope represents the resistance of the conductor. Just a little bit of a graphical way we can try and determine the resistance of a conductor. And just to reiterate, want to make sure we're comfortable being able to graph these simple relationships between, in this case, Ohm's law, between current and potential difference. And know that the slope of that line of a graph between current and potential difference would be the resistance of the conductor, or R. Now there's going to be several different factors that are going to play into how much resistance a conductor has, from the material it's made from to some other different factors that can be changed without changing the material itself. Now, in general, the resistance of a conducting wire is going to increase the longer that wire is, because now the current or electrons encounter and collide with an increasing number of atoms as they're moving along that conductor. So the resistance R of the wire varies directly with its length. I'll show you a little example of this here. We have a conductor. This is our, looks almost like a little section of copper wire. We have an equation up here, which we'll talk about in a second. Now, we're talking about here the length of the conductor compared to its resistance. We said that they were directly proportional, length being in the numerator of our relationship here. So if we increase the length of this wire, we should see resistance go up. And now as electrons are trying to move through this wire, they're bumping into other atoms as they move through here. The longer that wire is, the more chance, or an increased chance for more collisions through the wire, which means that flow of electrons is going to encounter more resistance moving through the wire. The shorter we make that wire, the less resistance we have. Less chance for electrons moving through here to run into other atoms to cause resistance or opposition to the flow of those electrons. Now, one of the things I always think about with this relationship here is using extension cords. If you use a really long extension cord, what you're going to do is increase resistance through that cord. And we'll see once you have more resistance, we'll see this shortly here, once you have more resistance in a wire, the longer that current has to flow, the more resistance, and that's going to cause more heat. This becomes a fire hazard using really long extension cords to run heavy-duty machinery. Can cause cords to melt as they heat up from all the electrons that are moving through that wire, moving through that conductor. Now, another factor that's going to affect the resistance of our wire here is the thickness of the wire. So as the thickness of the wire decreases, there's fewer spaces between the atoms for those electrons to pass through. That's if we're looking at the cross section or down the wire through which the electrons are traveling, kind of like looking down a tunnel. The narrower that tunnel, the greater the chance for collisions occurring. The bigger the tunnel is, the less chance for collisions occurring. So the resistance of a wire is going to vary inversely with its cross-sectional area A. Let's see what that means. So we have cross-sectional area here. It is in the denominator of our relationship here between resistivity, length, and area. So this is going to vary indirectly with our resistance. Now, if we increase the area or make this what we call gauge bigger on the wire, make that tunnel bigger, we should see resistance go down because now our electrons have more area to move through without encountering as many collisions. So thicker wires, thicker conductors are going to have a lower resistance because those electrons are going to encounter less atoms to collide with to cause resistance. Now, if we make that wire thinner or the gauge smaller, we can get to the point where we have extreme amounts of resistance, so big to the point where this R is literally filling up the screen because this wire is so small. There's so much resistance in here because the electrons that are passing through here are encountering a lot of resistance because they're colliding a lot with the atoms that make up the conductor. This is why we don't use small gauge wires, let's say on your refrigerator. We're not using really thin wires that you might have on your headphones to power your refrigerator. I know we have wireless headphones now, but you know what I mean. We use a thicker gauge wire because there's less resistance to handle the amount of electrons that are being used to power your refrigerator. So the more electrons or the more current that needs to be used by a device, the thicker wire we use, because there's less resistance, and therefore we can operate that item without having heat become an issue. So we have resistance increasing when the cross-sectional area decreases, and we have resistance decreasing when the cross-sectional area increases. And I'll put this in here for the resistance with length. As the resistance of the wire goes up, the length goes up. And as the resistance goes down, the length goes down. Now, resistivity itself is an actual property or characteristic of a material that depends on its electronic structure, how its atomic structure is set up, and its temperature. So resistivity meaning how the electronic structure is set up in the particular element or in the particular substance. It's going to have a different opposition to the flow of current just based off of how those atoms in that substance, in that conductor, are put together. And this is going to vary greatly depending on the temperature of the substance or of the conductor itself. Now, there are resistivity values given to you on page 4 of your reference table. So make sure you know where those values are located so you can use those. And looking at two different values on there, the nichrome wire compared to silver, nichrome has a much higher resistivity compared to silver, and therefore nichrome has a higher resistance than silver, because silver is not going to oppose the flow of electrons or have as much resistance in the structure of its atoms compared to nichrome. And all those values there are given to you at 20 degrees Celsius. As we increase the temperature on either silver or nichrome, the amount of resistance that electrons will encounter will increase. Now, the equation we can use for resistance, accounting for resistivity of a substance, is what we saw in the simulator, or PL over A, where P is the resistivity in an ohm meter, or a ohm meter. L is length, measured in meters. A is cross-sectional area in square meters, or M. And R is resistance in ohms. Now, just to kind of touch back here with the resistivity, if we just look at resistivity, it's going to be directly proportional to resistance, just like length was. And if we have something with a high resistivity, let's say like nichrome, these little black dots start to increase in here. And this is almost kind of like roadblocks that electrons will encounter as they come through here. The more roadblocks you have, the more collisions, the more resistance. Silver has a lower resistivity, which means there's less roadblocks for those electrons to encounter as they move through here, which means less resistance. So this value, the resistivity, is going to depend on if we want to lower resistance of our conductor, we essentially have to change the temperature or the material itself to lower the resistivity. This is oftentimes why computers and other electronic devices are run in cold temperatures, because the resistivity decreases, resistance decreases, and therefore are more efficient to run at colder temperatures due to less resistance. We have more of our input energy being used the way it's supposed to, as opposed to heating up our material as we're passing electrons through them. So the resistance, we said, was directly proportional to its resistivity. Or resistance goes up, resistivity goes up, resistance goes down, resistivity goes down. Now, good conductors are going to have low resistivities. I spelled that right. Good insulators are going to have high resistivities. Now, these are different. One's saying conductor, one's an insulator. So conductors are going to want a low resistivity, so we have low resistance. And a good insulator is going to want high resistance, so therefore it's going to have a high resistivity. As the temperature of the conductor increases, its resistivity is going to increase as well. Now, a resistor itself is a device that we can add into an electric circuit that is designed to have a definite or specific amount of resistance. And oftentimes these are little electronic components that look something like that, and would then have a series of different colored bands on the resistor, which would indicate the amount of resistance in that resistor. These are then added into different electronic components to achieve certain currents, voltages, etc. Required in that circuit, which we get into more in our next lesson. Now, these look like, this is out of your reference table, something like that. That's going to be our schematic symbol for a resistor. And we can find that on page 4 of your reference table. Now, a variable resistor is a coil of resistance wire whose effective, or essentially output resistance, can be varied by sliding a contact point. And this is going to look similar to the regular resistor, except now this one has draw that a little bit better, an arrow over the top that indicates essentially where the resistance is. Is it more? Is it less? Because we can change the amount. It's a varying amount of resistance. And the best example I always think of with this is a light dimmer. If you got a dimmer switch at home, you turn that, and the light output may increase, it might decrease depending how you turn it. But as you turn it, you're moving that contact point, and the more resistance we have, the dimmer the light gets. The less resistance we have, the brighter the light gets. So that would be a variable resistor. You might also see that as well in a fan. Now we'll do a little example here. Finding resistance of a conductor. Now we're looking for the resistance of a 5.52 meter length of silver wire having a diameter of 1.5 millimeters. We'll assume a temperature of 20 Celsius. So we know the length of the wire is 5.52 meters. We know that the diameter of the wire is 1.50 millimeters. And we know that temperature is 20 degrees Celsius. We also know that we're dealing with silver wire. And therefore, we know the resistivity of silver because it's given to us on the reference table. And that's going to be ohm meters. So we can find resistance. That's what we're looking for here. We can find resistance using our resistivity equation. We know the resistivity, we know the length, but in order to find R, we need the area, the cross-sectional area of the wire. Well, what we have here, it's a diameter of wire, and we know, well, actually this is the radius. We know the whole diameter here. This is 1.50 millimeters. So to find the area of a circle, we use pi r squared. And this is given to you on page 5 under geometry and trigonometry of your reference table. You might also just remember this one. So this comes out to pi 1.50 millimeters squared. We get a value of 1.77 times 10 to the minus 6 meters squared. And that's our area. We have a little intermediate step here. Now we can plug in and figure out what our resistance is here. We know that the resistivity is 1.59 times 10 to the minus 8 ohm meters times the length of the wire, which is 5.52 meters. We'll bracket that. We'll put that over our area, which was converted here in our calculation to meters. We want to make sure that that is the same. That was converted in our calculation. We plug all that in here. We get a resistance of 4.96 times 10 to the minus 2 ohms. If you guys have any questions on this, make sure you write them down and bring them to me so we can go through them and get your questions answered. Hope everyone has a great day.